In this video, let's take a look at a simple trace for Shellsort. Note that I'm not going to work this entire thing by hand because it's really complicated and because I'm not going to expect you guys to do it either. Okay, so we're just going to go through the visuals on the slide to give you guys a little bit more of a sense of how things move around a bit. So let's say we start with something, right? This is some sort of an input data, right, to my Shellsort algorithm. So sort example, 11 elements. So initially, I'm going to have to pick some sort of a gap sequence, and there is a formula, and when we see the algorithm, we'll see how we calculate this. But I need to start basically with some sort of a gap sequence that tells me how far away I should compare things. And I'll go through that, right, and basically try sorting this thing, and I'll shrink my gap, shrink my gap, shrink my gap, until I get to something that looks like insertion sort. So initially, right, this is step, essentially step 0, right? This is me having, nothing, right? I haven't done any sort of sorting. Then step 1. So step 1 would be a 7 sort. There's something called, so here, we'll go through a few of these different sorting passes. This is what we call basically a gap sequence. So the first number in our gap sequence for sorting this input of size 11 is 7. Okay, and there's a way basically you generate that gap sequence that tells you you're going to do this size and this size and this size and this size and this size. It's not arbitrary. It's not arbitrary. All right, so we're going to do a 7 sort. A 7 sort means that we're going to look at our inputs and compare elements that are 7 places away from one another. So like over here, we're going to end up comparing basically this first position with this position 7. So yeah, we're going to compare S and M. Well, in this case, right, they're out of order, so I flip them, right? So in my notation, my red is basically like the final resting place of an element. So in insertion sort, right, it's like we're going to push something and do exchanges until we get to where we want to belong. That's indicated in this notation by the fact that some of the letters are red, right? So it's like, that's as far as I went. I don't need to push M anywhere else, right? I kind of start by doing my insertion sort here, right? Basically on M, right? And M goes to the left, and well, it only goes one position, right? Because that's as far as it can go. So yeah, M gets placed there right at index 0. So we did that, right? And then we can basically go and repeat our process, right? We're going to do kind of more sorting, right? Again, we look at elements, right? So we're looking in this case, these over here, right? O and P. Those two are in the same order, right? So that we can just leave alone. L and R, those two are out of order, right? So we'll swap, we'll try to push to the left side so that L gets pushed over to where the R was on the right. Again, over here, we're doing another comparison with that gap in between. E gets pushed to the left, okay? So we've made kind of this pass through my array, right? Where I basically just check these things, right? See that there's 7 elements between them, right? But I want to know, right? Those two things on either side of that block of 7, are they in order or not? If they're not, I got to swap them. And so somehow, right, there's a sense here that this thing over here, right, is more sorted than this, right? This is less sorted over here, right? If I were to count the number of versions, and I'm not going to do it right now. You can do it if you want. But if you look at the number of inversions, this top thing has a lot more inversions than on the bottom, right? We've done some good here, right? So it's like this E element. This E element, it's going to be at the beginning-ish, and initially it was at the end. Now notice it's already migrated over here. So somehow, right, our lower letters are migrating over here, our higher letters are migrating over there, right? And that's what we want to see. So we're getting a little bit closer towards our goal of having a sorted array. So we've made some progress. We're not quite done. Let's shrink the gap. So now we'll go to 3. We'll do a 3 sort. So things are going to be a little bit more detailed, if you would. So here, right, we're looking at these elements and notice that they're now 3 positions away instead of 7 positions away. So E and M, right, basically I'm starting at M, pushing to the left. Those get exchanged, right? E basically ends up, E started over here, right? Now E ended up over there, right? So E got pushed, M got, basically sent to the right-hand side. So yeah, we repeat the process. Here we are looking at these 2 positions here. The E that was in the position where O is, right, that got pushed to the left, right? Because remember, so this is my starting, right? This is my starting data, right? And it's as I'm looking at elements, right? I'm pushing them to the left, right? So here, right, E got pushed to where it's at. E also got pushed to where it's at, right? We're pushing them to the left, Let's see, X stays the same. M, let's see, so M was originally occupied by A, right? So A got pushed to the left. And then there was an E there originally. The E got kind of pushed aside, and then A got moved forward, right? So here for the first time, right, we're basically doing 2 pushes. Here, right, here we basically have this, we just did it once, But here, because our gap distance is smaller, if we're looking over here at M, we can basically have 2 gaps in there, right? So we actually do 2 exchanges instead of just 1. So yeah, repeat the process, right? S looks like S stays where it's at, X stays where it's at, R stays where it's at, T stays where it's at. I know, so X is the only one that moves, right? So X is usually occupied by P, and then it does the exchange there with those 2. So yeah, so kind of over here, if you're looking at this, it's like each of those, right, is ones you're looking at, right, you're pushing left, pushing left, pushing left, right? And as we get down right here we can only push the maximum of twice, then here we can push it to the maximum of well, here the first time we can postulate like a maximum of 1, so then this is going to be a maximum of like 2, and then this should be like 3. I'm just ballparking it here. So yeah, and at the end, right, we have something that's actually not bad, right? It's decent sort, right? A is the beginning, X is pretty close to the end. It looks pretty good. So yeah, and I'm going to make a note over here to the side, right? So this is basically started with a 7 sort, then did a 3 sort, and now we're going to do a 1 sort. We always got to finish with a 1 sort because otherwise we don't know whether it's actually like sorted. You know, it could just be a little bit off. 1 sort is basically, well, it is, 1 sort is exactly insertion sort, right? So once we're done doing insertion sort, we know it's going to be good to go. So this is basically a diagram, kind of like we seen earlier, of tracing insertion sort, where we're just going and we're tracing it, you know, taking each element, pushing to the left, pushing to the left, right? So we're working along the diagonal here, right? Touch every element, compare with its neighbor, move it to the left. And notice there's not a whole lot of movement here, right? Like here we're moving 1, 1, 2, no move, 1 move, 2 moves, no moves, 1 move, 2 moves, 2 moves. It's basically no work at all to do, right? So this is going to be something that looks like O of n, right? So that'll be a very, very nice thing to do. So overall, right, what's happened is we've started with this kind of complete unordered example. We've started by basically taking things that are far apart from one another, right, that probably are responsible for a lot of inversions, and swapping them, right, to get an array that's a little bit better ordered, right? Doing this again and again and again, shrinking our gap, and basically we're converging over time to get to the sorted result. So yeah, that's basically what we can expect to see from Shellsort. As another quick visual, this is the final result, which is like, obvious. This is kind of how your data will flow, right? And we'll look at an animation later, but just as kind of some thoughts here. In general, your input looks like this, right? So maybe it looks something that's like random. And as you do your sorts, right? As you do your gaps, right? Right here, right, we're starting with 40, then we go 13, then 4, right, and then 1. Like initially, right, your input's completely random, then you do the 40 sort. It gets a little bit more sorted, right? So all of a sudden you notice, right, that smaller things end up on this side, larger things end up on this side, right? So it's like you're kind of slowly, you know, shuffling it around to be in a proper position. Then when you do that finer granularity sort, when you do that 13 sort, again, smaller things over here, larger things over here, and it gets better and better, right? So it's like over here, this was kind of, you know, a little bit far from where it belongs. Maybe this is far from where it belongs. Now all of a sudden, you know, things are looking a little bit better, right? As we get down to that finer sort, and as we go even down to 4 sort, it gets even better, right? So it's like now it's, you know, practically sorted, right? It's almost there. Then we do that final insertion sort pass, we're done. So overall, right, if you look at this thing, basically what you expect is that it converges, right? So initially you start with noise, right, just random data, and as you do that gap sorting, right, you shrink your gap, your smaller things migrate to the left, your larger things migrate to the right, right? And as the gap gets smaller, that migration, right, becomes finer and finer and finer until you basically converge on having an entire sorted array.